Okay, so today we're going to talk about the sets of numbers, and this should have been something you looked at in pre-algebra, but we're just going to make sure that we have things kind of clear and worked out. So you should have your notes in front of you, and so we're going to start with natural numbers. So the symbol for natural numbers is just a capital N, but then the first part has like a double bar with it. And roster is just a fancy name for list, just like you would have a sports like team roster, or we have a class list roster. It's just a list. So the roster is the list of numbers in that set, and the natural numbers starts with 1, 2, 3, and then we show a dot, dot, dot to show that that continues in that direction, and we put little set braces around it. Notice that that does not continue lower, it just continues in the direction higher than 3, because the natural numbers are your counting numbers. So examples of your counting numbers: 1, 2, 3, 7, 200, 4,000, numbers that would involve counting. Now they could be in different forms, like if you have the number 8 over 4 that's equal to 2, that is a counting number or a natural number. Now non-examples would be 0. 0 is not a counting number because you're not counting anything. We have 0, you have nothing. Negative numbers would not be counting numbers. And square roots that don't come out to specific counting values would be non-example. Like the square root of 2 is irrational. Now if you do have like the square root of 9, which is equal to 3, that is a counting number. So we'll move to the next set. And so we have the whole numbers. Again, the whole numbers, capital W, but then we have a little double bar. Now that should be a bar. Sometimes the whole numbers is just like a fancy script W. And roster is that list. We show little set braces. The only thing different about this roster is it includes 0. So we put 0 in the beginning, and then we have dot, dot, dot. So your whole numbers are your counting numbers or natural numbers and 0. So I like to think of them as the counting numbers and the one that looks like the whole, which is the 0, kind of looks like a whole, other kind of whole. And examples then, okay, so we have just 0, 4, 32, no negatives here. Again, you could have the square root of 9, which would be 3, so just keep in mind you could write them in different forms. 4,000, anything moving up there. Non-examples would be your negatives. Other non-examples would be your fractional values, like no decimal fraction or decimal pieces in the whole numbers. So you like 2.5, not a whole number, or negative 7.1, not a whole number. Whole numbers, again, just like whole pieces, no fractions or decimals. All right, and again, then we'll move to the next slide. So our next set is integers, and the symbol for integers is a Z with a double bar. Almost looks like a capital I for integers, but it actually comes from the German word Zahlen for number, but it is a Z with a double bar. And integers are your whole numbers and their opposites. So I'm just going to put that definition in there a while. Whole numbers and their opposites. And so again, no fraction or decimal pieces, no little leftovers in integers. Now for your roster this time, I'm going to take that and for the roster, we still do a list, but what you'll need to notice is we do have the ellipse or the dot, dot, dot in 2 directions. So we're going forever low and forever high. my little set braces there. I gotta squish those in. There we go. So just we're going in two directions for the roster there, so you just want to make sure you notice that. Examples of integers, the same as for counting numbers and natural numbers. And, so you could have those. You can have your square root of 9 again, which is 3. But this time we could also have the negative values, or like the opposite of -2 is +2, or you could just have -2, or anything positive or negative. No fraction or decimal pieces. Non-examples would be 6.3, or again the square root of 3, which would be irrational, or negative 7.1. No fraction or decimal pieces. So rational numbers are the next set, and the symbol for rational numbers is a Q, which seems a little weird because it's rational with an R, but the Q stands for the word quotient, which is the answer to a division problem. And rational numbers is any number, or an irrational number is any number that can be written as a ratio of two numbers. And like a ratio as in like 1/2 that's division, and that's where that Q comes from. This is not part of the definition, but just kind of leading you to that symbol of Q in there. And we don't show a roster for irrational numbers just because there's you can't do the list because there's so many little fraction decimal pieces. You could always add another little decimal to it. Like you could have, you can have all the counting numbers, 1, 400, all the negative values, but then you also can have 2.3, or negative 2.34, 7, like, so that's why you can't do the roster, because you could just keep adding little decimal pieces of that. Non-examples of rational numbers would be things that repeat, that do not repeat, things that go on forever without repeating, like pi, or the square root of any prime number. Okay, so if a decimal repeats, like if you have 4.9 repeating, that actually can be written as a fraction, and so that is a rational number. So we come to the set of irrational numbers, and the symbol for irrational numbers is a Q with a line on top, which we'll look at several times through the year as that line being the complement of, or in other words, not. So I'm just going to draw that. That's not part of the symbol, but that little line on top. So it's basically saying not rational. Again, there is no roster for this, so we will eliminate that part. And the definition of irrational numbers are numbers that cannot be written as a ratio of two values. Now, those are not quite as easily recognizable, but basically it's going to be things that you can't write as a fraction. So it's decimals that don't repeat and go on forever. So decimals that don't repeat in a pattern and they don't terminate, or that's just a fancy word for stop. So irrational numbers, kind of the opposite of the rational numbers, you would have like the square root of any prime values. You would have things like pi, which goes on forever without repeating. Non-examples would be anything rational, like things that you can write as a fraction, decimals that stop, decimals that repeat in a pattern you can write as a fraction, so those would be considered rational, not irrational. All right, so the last set we need to go over is the real numbers, and that really kind of encompasses all of them that we'll be doing this year. There are things called imaginary numbers, but we won't address those at this point. And the set of real numbers, again, is just kind of that capital letter, but this time with a double bar. Or sometimes you'll just see it written like just like a really fancy R. So much for my handwriting there. No roster. The definition for real numbers is kind of the combination of the set of all rational and irrational numbers. And basically, this is going to be any numbers that you know at this point in time. Non-examples are the square roots of negative numbers, which technically don't exist. So again, we're not really going to deal with things that are not real numbers at this point in time. So the next part of your notes, just the flowchart Venn diagram, that's really just organizing the sets of numbers into a Venn diagram. So we will typically kind of just create an overall set for the real numbers, and you have your symbol for your real numbers. And then inside the real numbers are two sets, and that is for the rational numbers and the irrational numbers. And irrational numbers, kind of the numbers by themselves, that's that non-repeating in a pattern, non-terminating decimals. But inside the rational numbers, we have the other sets. So inside the rational numbers, we have the set of integers. And inside the set of integers, we have the whole numbers. And inside the set of whole numbers, we have the natural numbers. So when you have a natural number, like the numbers 2, 3, 4, etc., those are also whole numbers, integers, and rational numbers. And then whole numbers we have 0. Integers we have the opposites, but no fraction or decimal pieces. And then we have our rational numbers that we can have, like our fractional decimal pieces. And let's just put an irrational over here. So we have an example. So we look at the next part, and we have a chart here. And the idea would be to be able to classify those numbers as, into the groups to which they belong. So typically we'll just put an X in the box if a number belongs to them, or you could do yeses and nos. I will typically show you with X's. Now all of these numbers are examples of real numbers, so I'm just going to mark down an X in that they belong to real numbers. And then we need to decide between rational and irrational. And it can only be one of these. Between rational and irrational. So as we look at our choices, pi is an irrational number. And the other values are rational. We have 0 is a rational number. It can be written as a fraction, 0 over 4, 0 over 5. 11 is rational as well. 3/8, obviously a fraction. 3.51, that's 3 and 51/100ths. That could be written as a fraction or mixed number. Now 2.17 repeating is a repeating decimal, so that can be written as a fraction, so that's rational. And -6 is also rational. Now we look at the values individually. So I'm just going to kind of draw a split down here because these could be more than one category over here. You just have to look at what they are. 0 is not a natural number, but it is a whole number and an integer. 11 is a natural number, a counting number, and so it is also a whole number and an integer. Now one way to look at this is to kind of go back to your Venn diagram, and if something fits inside the natural numbers, it is also inside whole numbers, integers, and rational. So you know it belongs to all of them. 3/8 is not a natural number or a whole number because it has that fractional piece, and it is not an integer because it's not a whole number or its opposite, so that is only rational and real. Same thing for 3.51, just rational and real. That fraction or decimal piece right there keeps it from being an integer. Same thing with the repeating part here. -6, not a natural number. You can't count in negatives there. Whole number, no, because of the negative. No negatives in the whole numbers, but it is an integer. And then because pi is irrational, it does not fit into those other categories as well. So taking a look at those and where they belong, comparing that to the Venn diagram on your own, and again, bring any questions you have to class. So the next part that we're going to talk about is just changing repeating fraction, or repeating decimal to a fraction. So you just need a plain piece of paper, or if you've got a spot on the back of the notes that you have, you can use that, but you just need a little open space. So we're going to talk about writing a repeating decimal as a fraction or a recurring decimal. So let's say you have the decimal 0.5 repeating, so that's 0.55555 on forever. Technically, to convert this, which is what I'm going to show you, you're saying, okay, so let's say n is equal to that repeating decimal. You know from equation solving that you can multiply both sides of an equation by the same thing. We're going to multiply both sides of this equation by 10. Now the reason we do that is we want to move the decimal point one digit, to have the repeating part slightly to the left of the decimal point. And so to move that decimal point one place, we have to multiply by 1 power of 10. If we would have two digits repeating, we would multiply by 100 because that would move the decimal 2 digits. So basically a power of 10 for how many digits are repeating after the decimal point. That would give us 10n on the left and 5.5 repeating on the right. Then we subtract n from both sides, but on the right we're subtracting what n is equal to, which is 0.5 repeating. So we said that n is equal to 0.5 repeating. We're subtracting that n from both sides. We get 9n is equal to 5. And then again, from equation solving, you can divide both sides by the same value. Those would cancel. And so we get n equals 5/9. So let's look at that again with, something that's not just one repeating digit. Let's say we have the number, 2.035 repeating, and it's that 3/5 repeating. So that's what we make equal to our variable. Say, okay, that's, and we want to move the decimal point, and in this case we actually want to move the decimal point 1 to 3 places to the left, so that we kind of encompass getting it past those 2 repeating places. Now moving the decimal 3 places to the right means we have to multiply by 1,000. So we're going to say, okay, times 1,000. times 1,000 on both sides of the equal sign. So that gives us 1,000n. And then here we have the 2, and then we have 0, 3, 5.35, and the 3 5s would go on forever, but we move it past 2 of them. Then we want to go on and we want to now see on this one, if we just subtract n from both sides, we're not going to get rid of the 0.35, so we have to do a little bit of a different step there. In this case, we need to multiply what we're subtracting by so for this one, in order to subtract off the pieces that you need to, we need to, instead of just subtracting 1n from both sides, we subtract 10n from both sides, because there's those 2 repeating digits, and we need to get that decimal over there to kind of get that repeating part off of both sides. So when we subtract that from both sides, we get 990n is equal to 2015, and then to get the n by itself, we divide both sides by 990. And then we would need to reduce that fraction. And when we reduce that, we get 2 and 7 over 198. So basically doing this by kind of the equation solving method, you want to multiply by a power of 10 based on how many digits repeats. So 1 digit repeating, 1 power of 10. To get that decimal past there, here we have 3 spaces, so 3 zeros that we're multiplying by. Then you want to subtract off the repeating part, so subtracting off the repeating part. So sometimes that's, just subtracting off the n, sometimes it's subtracting off something with the power, and then divide both sides by the coefficient of the n and reduce. And we will go over this in class as well. Bring any questions to your math teacher, and we'll talk about this tomorrow.